Okay, I will present this work on how to use global heuristics for multi-agent planning. This is actually a work, part of the PhD dissertation of the Alejandro Torreño, the first author here. Okay. Now, I will first make a short presentation on some map approaches that use local heuristics, or typically use local heuristics. We have, for example, goal approaches that apply goal allocation, where agents solve the allocated goals, and then the resulting plan is passed on to the next agent. Here, typically, agents apply local heuristics for solving the problem. We have also approaches that use plan merging, where agents synthesize a plan for their planning task, typically involving only the private information, and then local plans are globally coordinated. And then we have also other approaches that interleave planning and coordination, where agents maintain a separate search tree created with its own operators, and when an agent finds a node that contains public relevant information to another agent, then it's transmitted. And here, typically, local heuristics are applied to these search spaces. In contrast, sorry, FMAP is a multi-agent planner that applies global heuristics in a distributed search scheme. By global heuristic, we understand a heuristic estimator for a map task carried out cooperatively by several agents, which have partial knowledge of the task and possibly privacy requirements. By privacy, we mean here that there are some parts of the task unknown to the agents for whatever reasons. Here is one example on how to show privacy and the need of global heuristics. We have here one agent. We have the blue agent, which is a travel agency that moves around a geographical area. We have also another travel agency in red, which moves around the geographical area surrounded by the red circle. And then we have a factory, which is a functionally different agent. So the goal here is to transport the raw material located in L2 to the factory. So if we apply local heuristics, then each agent will only be able to evaluate the part of the planning task that they view. However, if we want a global evaluation of the plan, then this involves some communication machinery between agents to transmit the information and the evaluation of the unknown parts of the plan. So FMAP is a forward partial order planner. Nodes are flow-free partial order plans, and we keep only a single tree, but agents have different view of the tree. So here you have the first expansion of the tree, where the blue agent generates two nodes, which corresponds to two actions that are supported with the information of the root node, and equivalently for the red agent. We continue expansion, assuming we pick plan P2 for expansion, because the agents continue expanding the plan, and then we end up with nodes like this one here at the bottom, where this plan is contributed by several agents. So basically what we have is one agent responsible for the evaluation of a node, which is the agent that inserted the last action in the plan, and then this agent requests the evaluation of the unknown parts of the plan to the other agents, and then sends the node, and the evaluation sends out the node and the evaluation to the rest of agents. So in the heuristic evaluation, what we do is we evaluate each partial plan of the tree, but we use state-based heuristics applied on the frontier state of the plan. The frontier state is the state that results from executing the actions in the plan. Note that we are working with flow-free partial plans, so these are consistent states. So the heuristic is basically calculating the cost of reaching the variables in the goal state from the frontier state, and we use two different heuristics, one based on DTGs, domain transition graphs, and the other one based on landmark-based heuristic. First thing to say is that FMAP, the planning information, is represented internally with variables. We only use variables. So domain transition graph, we keep one domain transition graph per variable. Is a graph where nodes represent the values of the variables, and the transitions represent, the edges represent the transitions from one value to another value. DTGs are state-independent graphs, so this can be a static structure that can be calculated at pre-planning, and is privacy-preserving. The details can be found in this other presentation. So what we basically do is find a relaxed plan for the variables in the goal state from the frontier state, and then we count the number of actions, and the actions in the plan are estimated according to the information in the DTG. So this heuristic is very similar to the content and hence additive heuristic, but we work with DTGs rather than causal graphs. So basically, this heuristic works as follows. To estimate the cost of a goal in a one state, this is approximated as the minimum cost action that produces that goal, taking into account that all rest of preconditions G prime of the action related to the same variable as G are estimated in the same state, and the rest of preconditions set X of the action which are related to a variable other than the variable of G can be estimated from a different state. So more particularly, what we do is we calculate the shortest path from the initial value of the variable in the frontier state to the final value Dn in the goal state by applying the distributed Dijkstra algorithm on the DTGs, and then find the minimum cost action that induces each transition in the path. So once we have the transition calculated, the path calculated, assuming this last action, An, that has one precondition, V prime, taking the value Dn prime, so then we can estimate the cost of this fluent either from the frontier state or either from any other state formed with the side effects of the rest of actions. So in other words, once we have calculated one path, we can reuse the path for further estimations. That's the same underlying idea of the content and hence heuristic. Regarding the landmark-based heuristic, this basically consists in distributed generations of the landmark graph. It's also a static structure calculated at pre-planning, and is privacy preserving in the sense that agents only view the landmarks that are known to them, the public landmarks. And then the heuristic is just to count the number of landmarks, the non-rich landmarks in a plan. So here we have an example of how the landmarks are extracted, assuming this landmark in green color, which represents, for example, goal of the problem. We have in blue the information of one agent, in pink the information of the other agent. So what we do is they group the producer actions for this variable 1 on the landmark, and they exchange messages to find out that they have one common precondition related to variable 2 with the same value, and this is labeled as a public landmark candidate. They also find out that they have one non-common precondition related to variable 3, two different values, V3 and V4 respectively, and this is grouped as a disjunctive landmark. In this disjunctive landmark, the fluent variable 3 with value 3 is private to the blue agent, and the variable and the fluent variable 3 value V4 is assigned to the pink agent. So once we have the landmarks graph, what we do is we verify the single landmarks. We apply a distributed relaxed planning graph, and this is basically agents sending out all the public landmarks at once to the rest of agents. Agents receive those public landmarks, incorporating their own relaxed planning graph, and continue expanding until no new landmarks are found. So how is this used then for the heuristic evaluation? Assuming this landmark graph, in green color we have the landmarks already achieved in the plan. Then we have the blue agent who has 2 private landmarks plus the one public landmark. And then we have the pink agent who has 3 private landmarks and 1 public landmark. So what they do is they send out the landmarks, masking the private landmarks through a global identifier. The coordinator agent receives the information and counts the number of non-achieved landmarks in the plan. So what we do here is we alternate. We apply a combination of heuristic alternating, both heuristics, which has been proven to work very well in planning, and we just select the most promising plan according to the currently used heuristic, ignoring the other heuristic estimate. Basically, we keep 2 lists. In one list, nodes are ordered according to the DTG heuristic, and in the other list, nodes are sorted by the landmark heuristic. So this list represents the preferred successors. A preferred successor is a plan which contains a fewer number of non-rich landmarks than the parent node. So every node is maintained in the DTG list, and only preferred successors are maintained in the landmark list. agents extract and plumb from each list alternatively. Okay? Now, with respect to results, let's first make a comparison here between the multi-agent approach and the DTG approach, which is the basic or the main heuristic. Here, sorry. Here we can see that the coverage, which is the column sol, contains, in the case of the multi-heuristic version, it equals the number of, it equals or outnumbers the problem solved with respect to the DTG. Okay, and with respect to values here, we have a number of actions, make, span, and time. Values higher than 1 represents a better value for the multi-heuristic version, and values lower than 1 represents a worse results. So with respect to the number of actions, we can see here that values are very close to 1 in all cases, except here in the depots, which is, in the case of the multi-heuristic, gets a better results. With respect to make, span, also values are very close to 1, except in a couple of domains where they get better results for the multi-heuristic. And with respect to time, then this is variable results. We have some domains like depots or logistics where time is much better for the multi-heuristic, but in other domains, like here, we can see that the combination of heuristics actually we get worse results. But more interesting is if we compare the results of the multi-heuristic with the two standalone heuristics. Here we can see that the multi-heuristic version tends to mimic the best performing technique, the best performing standalone heuristic. For example, if we see here, in driver log, we have 15 problems. We have 15 problems solved in DTG and 7 problems for the land, and then in the multi-heuristic we get 15 problems. We have, for instance, the elevators. DTG solves 30, land solves 13, and the multi-heuristic solves 30. We can also observe the same with the open stacks, which is a domain which typically contains many landmarks, which in the case of landmark, heuristic solves 30, DTG solves 25, and the open stack solves 30. And also we can observe that when heuristics have, both standalone heuristics show similar performance, the synergy of both estimators tend to clearly outperform the results. For instance, in the depots, we can observe 8 problems in the DTG, 7 problems in land, and 12 problems in the multi-heuristic. We can also observe, for instance, 10 problems in the logistics in the DTG, 10 problems also in the landmark, and 20 problems in the multi-heuristic. So the synergy of both estimators, it's clearly outperforms then in the multi-heuristic. Then we did a small comparison of FMAP, our version, with respect to GPPP. This is just a comparison. Our aim was to see how FMAP was positioned with respect to a matrix-based planner. G3P is a matrix-based planner that uses the notion of privacy typically defined in matrix. It's a sequential planner, and doesn't use communication infrastructure. According to time, as you can see, it's clearly that G3P clearly outperforms FMAP. With the number of solved problems, we can see there are some domains where there are a couple of more problems solved for FMAP. And with respect to the number of actions, that shows better results for FMAP, thanks probably to the partial order planning paradigm. I would also to make just a mention of the results that FMAP got in the distributed track of the competition, and the difference of results between the competition and the ones I show here. Well, the main reason is because the loss of accuracy of our DTG heuristic. Because we had to convert our variable language of FMAP to predicates in MAPDDL. So basically what we did is to convert every variable, state variable, to a binary variable. So in order to show you the impact of what this means, here on the left, you have a DTG for a Sokoban task that represents the DTG of the variable position of a player. The nodes correspond to the locations of the player in the entire game board. And then the connections show how to go from one value to the other. And here on the right, we have one true-false DTG. So when we work with binary Boolean variables, what we get is a set of true-false DTG, one per value of the variable. So as you can see, there is a great loss of accuracy in the heuristic, especially in the DTG. Well, finally, we can say that alternation of heuristics shows very beneficial, also for multi-agent planning, and that global heuristics are worth as long as the gain of the heuristic pays off the communication cost, which on the other hand is necessary if you want to work with distributed environments with private information. We are thinking, we have to anyway to study, to analyze this and to look into converting the MA PDDL problems of the competition into PDDL 3.1. Okay, so just to overcome the limitation of the heuristic, we will investigate on this. And also another aspect that makes our planner to be slower than rest of planners typically is the use of, we use a message broker on top of a multi-agent system platform. So the idea is to, for this version I just presented here, to replace this broker by sockets and see if we can alleviate the problem of the communications. And this is it.
Thank you very much.